This is the 11th lecture and we are going to discuss mid frequency analysis of the common emitter and common base BJT amplifier. The common emitter amplifier circuit is, as you very well know by now, has an R sub C, R sub E, a bypass capacitor C sub E, a coupling capacitor C2 goes to a load R sub L. The voltage, output voltage is measured here, capital V subscript O. I am going to explain this symbol in a minute. This goes to plus VCC, and the base biasing, let us consider the usual biasing in which there are two resistors R1 and R2. The input signal is applied through a capacitor C1 from a source whose resistance we indicate as RS, and this is the source Vs. This is the simple circuit of a common emitter amplifier. The transistor is Q. Now, we have so far used three kinds of symbols. One is, let us take any symbol, let us say VCE. We have used capital V subscript capital C capital E as the DC voltage from collector to emitter. Okay, DC voltage. This is the DC voltage. We have also used the symbol small v subscript capital C capital E as the total voltage across the collector to emitter terminals, total voltage, and the symbol V sub small c as the incremental part or the signal part or the AC part, which means that capital V sub capital C capital E is equal to small v subscript capital C capital E plus minus or plus minus. Okay. What we used was VCE as equal to capital VCE, the DC part, plus small v subscript small e. This is the symbol that we have used. That is correct, small e. Please do correct me, VCE. Alright. Now I am going to use another symbol. The only thing that is reserved up till now is capital V subscript small c small e. This is the only thing that is reserved, right? I have used all other combinations, but it must be clear that throughout the course this is the symbol that we are going to use. Now, our signals will mostly be sinusoidal signals, alright. In the amplifier analysis, wherever we are considering a linear circuit, our signals will be AC, either a pure sinusoid or a combination of sinusoids. For example, if it is an audio amplifier, it is sinusoids starting from about 16 hertz to approximately 16 kilohertz. So, our signals are mostly AC sinusoidal signals, which, as you know, a voltage, an AC voltage is described by the maximum value times sine of omega t plus maybe some phase phi, where this is the maximum voltage. Okay, and you know that the maximum is root 2 times V max is root 2 times V RMS. Okay, and that for AC analysis we can use the so called phasors. Alright. Now, the phasor that we shall use in the context of this analysis would be either the root mean square voltage or the maximum voltage, so long as we are consistent, that is, if our phasors, if the voltage phasor is the RMS value, if the voltage phasor magnitude is equal to the RMS value, then all other voltages and all currents in the phasor diagram shall be RMS values. Otherwise they will all be maximum values. Okay. So we shall use this symbol as the phasor. Alright, capital V subscript small c small e will be the voltage developed from collector to emitter, the AC voltage or the signal voltage, it is which is represented by the phasor VCE. Is that okay? This is the symbol that we shall use throughout. Whenever we write capital I subscript small c, we mean the phasor corresponding to the AC voltage. Okay. So in equivalent circuits, for example, we shall use this particular symbol. Okay. Now since we are making an AC analysis or signal analysis, we can replace this by an equivalent circuit with the transistor replaced by its hybrid pi equivalent circuit. And since we are considering mid frequencies, all external capacitors C1, C2, Ce shall act as short circuits, and all internal capacitors like C pi, C mu and C0 will act as open circuits. Therefore our equivalent circuit would basically be a resistive circuit. Let us draw this carefully. We start from the source R sub S. Now we are using this symbol Vs to represent the phasor corresponding to the signal, and this phasor can be, as I said, either the RMS value or the maximum value, but you must be consistent. Okay. Then the capacitor C1 is a short. The parallel combination R2 and R1 shall come in parallel as far as AC is concerned. So we combine them into a single resistance R sub B. R sub B is equal to R1 parallel R2, usually a large quantity compared to what it faces. Now this is the external base B. From the external base to the internal base, as you know, there is a small resistance Rx, and from internal base to the emitter terminal there is a resistance R sub pi. The voltage across this we denote by V pi. Now this capital V represents the phasor voltage. Okay, the phasor voltage across R pi. Then we have a current generator which I can represent either in terms of beta or in terms of GM. So we represent this, we find it convenient to work in terms of GM because GM can be calculated from the Q point. It is 40 times I sub C in I sub C expressed in milliamps. Okay. So it is GM V pi, and then we shall have from the collector, this is the collector terminal, from the collector to the emitter we shall have the early resistance R sub 0, which is usually a very large value, large resistance, and then we have the biasing resistance R sub C. C2 acts as a short circuit and therefore RL comes in parallel. This is the resistance, load resistance RL, and it is this voltage V0 that we are interested in. V0 also corresponds to the phasor value of the output voltage. Now mostly what we shall be concerned with is the gain, V0 divided by Vs, alright, the voltage gain or the current gain. We can take the current through the load as our output and the current supplied as the input I sub I. Then current gain would be I0 divided by I sub I, and these are also phasor quantities. Or we could have been interested in the input impedance faced by the source. We shall call this as R sub I. Input impedance faced by the source, or the output impedance faced by the load, that is from the load end what is the impedance that it faces. We shall call this as R0. Okay. Ri obviously is if this voltage is called Vi, once again a phasor, if this voltage is Vi, then Ri is obviously Vi divided by I sub I. Output resistance, however, cannot be calculated like this, because there is a source here. For calculation of output resistance, you must connect a source here and find out the current that goes into this circuit. We shall see how to do this a little later, but you realize that all quantities that we are interested in is a ratio of one phasor to another. If it is a gain, then it's a voltage phasor by voltage phasor. If it is input impedance, then it's a voltage phasor divided by a current phasor, and therefore whether you take the maximum value or the root mean squared value, it doesn't matter. Root 2 and root 2 cancel out. The advantage of phasor is that it takes account of the magnitude and also the phase, and therefore we shall be in one thing that we want to do, one thing that we have ignored. What have we ignored in this circuit?
So R mu.
R mu we have ignored. Usually R mu is a very large quantity, and therefore we are justified in ignoring this. We will show this by means of a dotted diagram. R mu. If R mu is there, then you see, to solve or to analyze this circuit, we have to write three node equations. One is here, one is here, and the other is here. Three node equations, and we have to solve them. Okay, we have to invert a 3 by 3 matrix. Three node equations will mean there will be a coefficient matrix whose dimension is 3 by 3. We have to invert a 3 by 3 matrix to find out these voltages. On the other hand, if R mu is not there, analysis can be done almost by inspection, and this is what an engineer desires. By looking at this circuit, you should be able to write down the gain and other things. Let us see how to do this analysis.
Sir,
yes.
so can you just repeat on how you find the output impedance?
How I find the output impedance. Okay, given a circuit, any circuit, amplifier or otherwise, which is connected to a source and to a load, if I want to find the output impedance, what I will do is, output impedance is the impedance seen by the load. Okay, so what I do is, I first disconnect this RL and I connect a source here. Let's call this as VO, some voltage source VO, and find out this current I sub O by short circuiting the input source. Input source should not be there, it should be short circuited. If it is a current source, you open circuit this source. So you find out I0 in response to a V0, and output impedance will be V0 divided by I0. We shall calculate this for the amplifier circuit that we have just drawn. Now as far as the gain is concerned, this is the same circuit. What I do is, I first notice that the voltage V0, these three resistors are in parallel, so I could replace them by a single resistor of value R0 parallel RC parallel RL. No, but before that, okay, you notice that if I replace this by a single resistance, I lose I0. Isn't that right? The identity of I0 is lost, but V0 is not lost. How is V0 produced? This current passes like this through this single resistance, and therefore I can immediately write V0 equal to minus, because the current and this voltage, they don't agree with each other, so minus GM V pi times this equivalent resistance R0 parallel RC parallel RL. All right. Then the thing that remains to be found out is V pi in terms of, now I can define two gains. One is, I shall define AV as V0 divided by VI. VI is the actual voltage that is connected from the base to emitter, actual voltage that appears from the base to the emitter. This is one gain, and the other gain I will define as AVS, that is the output voltage divided by the actual source voltage Vs. There are two voltage gains, and if you know how to calculate one, it's very easy to calculate the other. We shall show this, but what I need is, if I want to calculate AV, then what I need is, I have an expression for V0 by V pi, so all I need is V pi divided by Vi, and don't you see by inspection that V pi is equal to Vi multiplied by R pi over R pi plus Rx. It's a simple potential division. Therefore, my gain becomes S of V becomes equal to minus Gm times R0 parallel Rc parallel RL multiplied by R pi divided by R pi plus Rx. Alright. Now you also know that R0 is usually of the order of a meg, and Rc and RL are of the order of a kilo, and therefore the parallel combination of R0, Rc and RL will be approximately the same as Gm RL prime, where RL prime is equal to RL parallel Rc. I have written an approximation sign, and you also know that Rx is of the order of 100 ohms and R pi is of the order of kilo, and therefore we can ignore this also, and therefore the gain simply becomes minus Gm RL prime. By looking at this circuit, we didn't write a loop equation, we didn't write a node equation, we did not invert any matrix. I calculated this only by inspection. Okay, this is, and now if I want to find out AVS, then all I need is AV is to be multiplied by Vi divided by Vs, and therefore this will be minus Gm RL prime. Now Vi by Vs, if you again look at this circuit, it is also a potential division, not Rb by, Rb comes in parallel with Rx plus R pi, that divided by Rs plus this equivalent. Okay, so it would be Rb parallel Rx plus R pi divided by Rs plus Rb parallel Rx plus R pi. Alright, and a very good engineering approximation would be Rb usually is a very large quantity compared to Rx plus R pi, is of the order of tens of k's. 34k was the value in our previous example. Rx is a small quantity, so this whole thing can be replaced by R pi, approximately equal to R pi, and therefore my gain becomes approximately, this is also an approximation, minus Gm RL prime times R pi divided by Rs plus R pi, and you know that the product of Gm and R pi is simply beta, and therefore this is equal to minus beta RL prime divided by Rs plus R pi, also by inspection, the two gains. As far as the current gain is concerned, what we do is, any question on this? No. Current gain is very simple. I0 by I sub I is simply V0 by RL divided by I sub I is, yes, Vi over Ri, the input resistance. Now input resistance, as you can see from the circuit, let's go back to the circuit. The input resistance is simply the parallel combination of Rb and Rx plus R pi. Okay, so I get V0 divided by Vi multiplied by Ri, pardon me, V0 divided by I sub I, yes, that is equal to, let me write it, Vi divided by I sub I, okay, that is equal to Rb parallel Rx plus R pi, and this is approximately equal to R pi, and therefore I0 by II, which I shall write as AI, the current gain, would be equal to AV, V0 by Vi, multiplied by Ri divided by RL, which is equal to R pi divided by RL. This is approximately the current gain. It's very easy to see that this is approximately equal to minus, is there a minus sign? There is a minus sign, okay, this is minus, no, AV is minus, okay, that's how it comes. And if you substitute for AV, what is AV? Minus GM RL prime, and GM and R pi make a beta, and therefore this is approximately minus beta RL prime divided by RL. Which one is greater, RL prime or RL? RL, and therefore AI, the current amplification factor, is now less than beta. The short circuit value is equal to beta. Beta is the short circuit current amplification factor. Whenever there is a load, the current amplification factor will be less. All right. Finally, we go to the output resistance. Let us see how to calculate the output resistance. Well, what we have is, let me draw the circuit quickly. Rs, then you have Rx, R pi, GM V pi, and then you have this parallel combination of, let me combine this into a single resistance, R0 parallel RC parallel RL, which is approximately equal to RL prime. Can I do that? No, I cannot.
You have to find out output resistance which is separate.
Which is faced by RL. Alright, so I cannot combine. I simply combine R0 and RC. For finding the output resistance is the resistance faced by the load. So you must decouple the load. Load is taken off, a voltage source V0 is applied here, and the current I0 is to be found out after short circuiting Vs. If we do that, then what is V pi? If I short circuit this, V pi obviously shall be 0. Agreed? So the current generator shall give a 0 current, and therefore R0 by inspection therefore is equal to R0 small r0 parallel RC, which is approximately equal to RC. That is the output resistance. Let us take an example. Any question on this? Let us take an example, a practical example. A transistor which is a 1K, a bypass capacitor, 6 volt source, a 2.2K R sub C, a coupling capacitor, the load is also 2.2K, no 4.7K. This is my V0, and I have the base biasing is done by 2 resistors of equal value, 220K and 220K. Then I have a capacitor, a source of resistance 600 ohm, voltage source, therefore resistance should be low, and a signal source Vs. This is the transistor Q, and what are given are, the parameters are given. GM is given as 39 millimho. What is the collector current? I sub C
Divided by 40.
approximately 1 milliampere. You will see it's slightly more because of that 26 factor. Okay, GM is given, R pi is given as 2.6 K, R pi is given, Rx is given 100 ohms, R mu is given as 13 meg, we ignored this, R0 is given as 139 K, we ignored that also, it's very large, 139 K. The capacitors are shorts. You are required to find out first of all the Q point, which means that you are required to find out I sub C and VCE, okay, and then all these gains, A sub V, the voltage gain, the input resistance R sub I, the current gain A sub I, and let us say the output resistance R0 and also AVS. These are the quantities to be found out for this particular circuit. The first thing that you have to find out is the Q point. Okay, let us find out the Q point. Yes. Question? No. As far as the Q point is concerned, our procedure is very simple. Our VBB, we first find the IB, the base current, and then multiply this by beta. So we have to find out the beta first. What is beta? Beta is 39 millimho multiplied by 2.6 K, and this comes out as approximately 100. This comes out approximately as 100. So in order to find out IB, our VBB is 3 volt, agreed, and R sub B is 110 K. Then there is a voltage drop from base to emitter of value 0.7, alright. Then this goes to RE, which is 1 K. All right, the current that comes here is how much? I sub C, which is approximately the same as I sub E. It is beta plus beta IB. It is beta IB, okay, and this current is IB. I have made a mistake. Can you tell me what the mistake is?
You have not drawn the source.
No, source I don't have to, I am making DC analysis. This symbol, this must be capital B. Capital I sub capital B. This is capital B. Alright, this is what we have.
So, how do we know if the emitter resistance is 1K? Its value is not being given.
Its value is given. Its value is given as 1K. You did not note it. Alright. Therefore, my I sub B, now it should not require, with a little bit of experience, it should not require drawing of this equivalent circuit. You should be able to do it by inspection. I sub B is simply 3 VBB minus 0.7 divided by the total resistance in the circuit. The total resistance is 110 K plus no. So 101 multiplied by 1K. Is that clear? Because the current in this is not IB, it's beta plus 1 IB. Now if I calculate this, it comes out as 11 microampere, and therefore my I sub C, the collector current, would be beta times this, which is equal to 1.1 milliampere. And if I know the collector current, then I know VCE. Let's not make a mistake. VCE would be 6 volt minus the drop in 2.2K and 1K, and this drop, the currents are approximately equal. So I multiply 1.1 milliampere by 3.2K, and this comes out as 2.5 volt. This comes out as 2.5 volts. This is perfectly okay. We can now go ahead with the calculation of the gains and input and output resistances. But let's look at this point of time whether this is a good amplifier or not, whether this is a good Q point or not. Okay, how to judge this? To judge this, we take the characteristics I sub capital C, V sub capital CE, and our DC load line is something like this. Starts at what value? 6 volt, and ends at 6 divided by 2.2 or 3.2? 3.2. So many milliamps. This is the load line, and the Q point is somewhere here. Q point has 2.5 volts, so it is somewhere here. This is 2.5, and the current is 1.1 milliamps. This is the Q point. We have to judge whether this is a good Q point or not. Now, to judge this, we require to draw first the AC load line, and the AC load line will have a slope of minus 1 by RC parallel RL, which is 2.2 parallel 4.7 K. What does this mean? It means, you know, the AC load line is a plot of this characteristic V sub CE minus VCEQ is equal to minus 2.2 parallel 4.7 K multiplied by I small I capital C minus ICQ. All right. To be able to draw the load line, AC load line, it is sufficient to draw a line through the Q point with this slope. It is sufficient. Isn't that right? Now let's see where this load line touches the, let us see where it touches this line. We want to find this to judge whether this is a good amplifier or not. Let us see where it touches. Now at this point, what is the value of the total collector current? It is 0. So this point will be determined by, if you put this equal to 0, then you can show by putting the values, numerical values, that VCE comes as 2.5 plus this quantity. This comes as 4.15 volt. All right. This calculation is numerical. You put VCEQ as equal to 2.5 volt and ICQ as 1.1 milliampere. All right. I am skipping this numerical calculation, but what it means is the following, that this voltage, this point is 4.15 volt. So what is the swing that is permitted? 4.15 minus 2.5, which is 1.65 volt. That is not enough. This is swing on the right side. What about the left side? If I go 1.65 volt here, where do we touch? 0.85. Is this a good point? Suppose it went to 0.2, then we would have been worried, because then the swing would be limited. But 0.85 is okay, it's far away from saturation, and therefore this is a good operating point, and it will be a good amplifier with a swing of 1.65 volt on either side, which means that the maximum AC signal that you can get out of the amplifier is 1.65 volt. Peak value the root mean squared value will be 1.65 divided by root 2. Is that okay? Now if you now find the gain, if you now find the voltage gains, then you will know what can be the maximum driving signal. Is that point clear? Output swing permitted is 1.65. So if you divide this by the gain of the amplifier, then you will know what is the maximum swing of the input AC. If you drive the transistor beyond this, then it will go to cutoff on one side. Alright, and if you drive further, then it will go to saturation on the other side. Is that clear? Okay, let us calculate the gains now. This I thought I would give you a pictorial representation and clarification of the AC load line. DC load line and AC load line are two very important characteristics of an amplifier. Once this diagram can be drawn, almost everything else will be clear. You will know what amount of AC signal can you put at the input. Alright. So now let us calculate the gain. Now it is a matter of applying the formulas, or you can draw the hybrid pi equivalent circuit and do things by inspection. Here S sub V, which is minus GM RL prime, would be equal to minus 39 millimos multiplied by 2.2 parallel 4.7 K, and this comes out as minus 58.5, and therefore you know the maximum VI, capital V subscript capital I, that can be applied. This is not the source voltage, because the source has a 600 ohm resistance. The source voltage may be higher. The maximum VI would therefore be, peak value would be 1.65 divided by 58.5. This is the maximum signal, maximum peak signal that you can apply to the input. Okay. S sub I. R sub I, the input resistance, is simply RB, which was 110 K, parallel Rx plus R pi. How much is that? 2.6 kilo is R pi and 100 ohms is Rx. So it is 2.61, even if you want to take Rx into account. RB is 110 so many kilos, and this comes out as very nearly 2.6. It is 2.54 K. Ignoring RB would not have caused much of a deviation. It is only 2.54. So 0.07 is in 260 is less than 3% deviation. Alright. This is Ri. A sub I, which is minus beta RL prime divided by RL, approximately, this comes out as minus 31.6. Beta was 100, so it is approximately 1/3. You lose in current amplification. You are asking for voltage amplification, so you lose in current amplification. Okay. Yes.
So how by the voltage gain did you figure out what input voltage did you apply?
Oh, if I know the output voltage peak value is 1.65. I divide by the gain, so this gives you the input voltage. After all, what is the definition of gain? Output divided by?
1.65 is the output voltage.
That's right, peak value that we found out from the AC load line. Okay, so the peak input that you can apply from base to emitter, this is not the source voltage, from base to emitter. Agreed? It's not the source voltage, because source has a resistance of 600 ohm. Source voltage would be higher than this. That also you can calculate.
Rx was 100 or 10, sir?
Rx I gave as 100 ohms. 100 ohms.
So
Yes.
then Rx plus R pi will be 2.7.
No, 100 ohms is 0.1 kilo,
Yeah.
and this is 2.6. Oh, okay. All right, I made a mistake. Sorry about it. This would be 2.7. So you can correct this. Thank you for pointing this out. I made a mistake. All right, what remains to be found out is R0, as you know, R0 is the parallel combination of small r0 here given as 139K. If the figure is given, you use it and show that it's negligible. This is parallel to, what should I parallel with? 2.2K, and this comes out as 2.16K. It's not very different from 2.2K. We could have safely neglected this. And AVS, what do you think this would be? Would it be greater than AV or less than AV? It would be less, because there is a potential division between RS and RI. Okay, this would be AV minus 58.5 multiplied by RI divided by RI plus RS. We have found out RI. RS is given as 600 ohms, and this comes out as 47.4 minus 47.4. You of course realize the importance of this negative sign. What does the negative sign indicate? That there is phase shift of 180 degrees. Okay. Any question about this example? Yes.
So if instead of RL, sir, we keep an open circuit, both the current gain and the voltage gain will increase, sir.
That is correct. Unfortunately, RL is not your choice. As I said, if this is a audio amplifier, for example, RL could be the loudspeaker, 8 ohms. Alright, 4.7K typically could be the input impedance of another amplifier to which you are going to fit this. One amplifier can give you a gain of only 60. If you require a gain of 1000, obviously you require another amplifier. And RL could be the input impedance of the next amplifier. It's not your choice. If you can keep it open, go ahead. Get all the gain that you want. Okay. Now a complication arises in this circuit if RE is not bypassed. If RE is not bypassed, let's draw this circuit again. RC, C2, RL, V0 minus R1 and R2, C1, RS and VS. Complication arises if RE is not bypassed. If this bypass capacitor is absent, you will see that in many circuits in practice RE is not bypassed. It's intentional. Why it is so, why it is required, we shall explain later. This stabilizes the gain. This makes the gain insensitive to variations of other parameters. But if it is so, how do we analyze this circuit? We shall show engineer's thumb rule. If the transistor, will prove this, but let me state this. Engineer's thumb rule is, if RE is bypassed, then the gain is approximately equal to the ratio of R sub C to R sub E. Approximately the voltage gain is approximately equal to this. If both the resistors are equal, 1K and 1K, then the gain is, no, I made a mistake. This is RC parallel RL. That is the equivalent load. If the equivalent load and RE are equal, then the gain is simply minus 1. Alright, we will see how this drastic reduction in gain occurs by drawing, as usual, the equivalent circuit. That is, you will see this makes a hell of a lot of difference whether RE is bypassed or not bypassed. We have the usual equivalent circuit R sub B, then you have Rx, R pi. Now we cannot take it to emitter because RE is not bypassed. So R pi shall go to RE, which goes to the emitter terminal.
That's a ground. This is ground. That's a emitter.
Thank you. This is the ground. From internal base to emitter, yes, the resistance is R pi, the voltage is V pi, and then we have here from collector to emitter we have Gm V pi, then we have, where is R0? Again between these two terminals, R0. Then we have from here to ground is R sub C, and in parallel with R sub L, this current is I0 and this voltage is V0. Now this creates a complication in the analysis, but several things should be obvious. First, that we can ignore R0, goes to infinity, so this is open, and the voltage V0 is still due to the current Gm V pi flowing through this combination. Agreed? That is, V0 is still equal to minus Gm V pi multiplied by RL prime. Is that clear? Is that clear? Okay. The same current, this current must come like this. If you combine this into a single resistance, V0 must be the drop in effective load RC parallel RL prime due to the flow of Gm V pi. Alright, this is by inspection. By inspection you also see, well, this voltage is Vi, what we need now is Vi. You see that the current through this resistance, what is the current? This is V pi divided by R pi. This current comes from the left, and from the right comes Gm V pi. So this is equal to V pi times beta plus 1 divided by R pi. Is that okay? Is it okay? Alright. So the drop across this is not due to V pi by R pi only. The drop across this is due to a current which is beta plus 1 times higher than V pi by R pi. So as far as the input is concerned, let's write this equation. I can't write it on the same sheet, but I hope you will remember. My equation is Vi, the input voltage, is is, let's say, V pi, just a minute, let's call this current as I1. Let's call this current as I1. Then it is I1 times Rx plus R pi plus beta plus 1 I1 multiplied by Re. Agreed? Is the point clear?
Yes, sir.
Okay, which means that if I look here, if I look here to the right, the effective resistance that I see is Rx plus R pi plus beta plus 1 Re, and therefore my input resistance, if I look here, then it would be Rb parallel this increased resistance, alright, which means that Ri is equal to Rb, stop me if you have not followed this, Rb parallel Rx plus R pi plus beta plus 1 Re, and usually Rb is large, Rx is small, and beta plus 1 Re would be much larger than R pi. R pi is of the order of a k, so is Re, but this is 101 times Re, so this will be approximately the same as beta plus 1 Re. But this large resistance is now being paralleled by another large resistance, so Rb you cannot ignore, this will come in parallel with RB. This is the input resistance. Can you tell me now from the circuit what is V pi? V pi would be equal to Vi divided by Rx plus R pi plus beta plus 1 Re multiplied by R pi, and therefore the gain of the circuit AV, which is equal to V0 divided by Vi, would be equal to minus Gm RL prime, and instead of V pi I should write this quantity, so it would be R pi divided by Rx plus R pi plus beta plus 1 Re. Is it okay? The gain now, as you can see, is reduced by this factor. The gain with Re bypassed. Re bypassed means what? Re effectively equal to 0. So this factor drops out, and R pi by Rx plus R pi is approximately 1, and therefore the gain with Re short circuited is simply this factor minus Gm RL prime, which we calculated a minute earlier. And there is now a drastic reduction of gain. R pi is of the order of a k, and this is about 100 k. Okay, 101 times Re. So the gain would be drastically reduced. Okay, so we have calculated the gain. This you can write approximately as, and as a simple expression now, minus beta RL prime divided by Gm R pi becomes beta divided by, if you ignore all this, then beta plus 1, ignore 1, beta Re, which means that this is approximately minus RL prime by Re. This was the rule of thumb that we had stated at the beginning of the analysis, that is simply the ratio of effective load at the collector to what you can consider as load at the emitter. This resistance Re is kind of a load at the emitter. But then an interesting sideline is the following. I want my circuit again. An interesting sideline is that yes, you can take the output from here, one output V0. You can also take an output from here. Isn't that right? And if these two resistors, if the effective loads are equal, if RC parallel RL is the same as Re, then these two voltages will have the property of equality in magnitude, but out of phase, opposite phase. All right, and pardon me?
Please repeat this.
Please repeat this. Okay, the voltage here and the voltage here are out of phase. Why? Okay, you have to calculate the voltage. Let's look at the equivalent circuit. The voltage here is the drop due to V pi by R pi times beta plus 1, and V pi is in phase with Vi, and therefore this voltage will be in phase with Vi. On the other hand, this voltage is out of phase with Vi. So the point that I was making is that this circuit can be used to get from a single voltage two voltages of equal magnitude and 180 degree out of phase. Such voltages are required in many electronic circuits. Two voltages identical magnitude but opposite in phase from a single source. All right. So in that, if it is that particular use, then it is called in literature as a paraphase amplifier. Okay, this is one of the uses of this unbypassed capacitor. The other use, as you can see, since the gain is RL prime by RE, you have made the gain insensitive to the transistor. It does not depend on GM, it does not depend on Rx, it does not depend on R pi. It depends only on these two external resistors. In integrated circuits, the ratio of two resistors can be very accurately tuned and can be made absolutely stable. Even though individual resistors may vary, the ratio with temperature or humidity or any other environmental variations, ratio can be kept constant, and therefore this is a configuration in which you can get a gain. RL prime could be 100 times RE, then you get a gain of 100. The gain is insensitive to transistor parameters. Even if the Q point shifts slightly, even if the transistor bias was not stabilized properly, even then this gives you a gain which is insensitive to transistor parameter variations. If you continue this calculation, we have already found out Ri, that is Rb parallel Rx plus R pi plus beta plus 1 Re. Now, what was the input impedance in the case of a bypassed amplifier? This term was absent and it was approximately equal to R pi of the order of a k. Now, if beta is 100 and Re is of the order of a k, you can get an input impedance of 101 k, right? Parallel another, let us say 101 k, so 55 k. This is a very large resistor. So this is one of the ways to increase the input impedance of the amplifier. Okay, unbypassing the emitter resistor creates a high impedance. So this has the property of high impedance. If you calculate R0, the output impedance, what do you think this would be? This would be the same as previous case. Where is R0 taken? Across the load, that is from the collector to ground, and this would be equal to R sub C. Can you tell me why? Why Re does not come into the picture? Let us take the equivalent circuit, then you will understand.
So because the current through Re is 0.
No?
So V pi is 0 there.
V pi is 0, but GM V pi that flows through Re.
Yes. But that is open circuit.
You see, what I am doing is I am calculating the impedance looking here, R0, and I am claiming that it should be RC. Yes? Why does it remain the same? Why doesn't RE affect it?
R0 is much larger than RE.
So R0
you
plus
open the,
RE, so
dependent-
R0 compared to
R0 plus RE, R0 is, let us say R0 is infinity. Take it off. You cannot combine R0 with RE because R0 comes in parallel with GM V pi. No, there has to be a fundamental concept.
This is showing the,
Because it is GM.
the current source is opened up.
So
there will be no current through Re.
no ground through it.
Okay, if I short circuit this, there is no current through RE. Why not? GM V pi.
So but V pi
V pi is 0.
V pi is 0.
But that is not the consideration. The current is 0, so what?
So you open that GM branch,
You see, this GM V pi is a current source. What is the internal impedance of a current source?
infinity,
Infinity.
What is infinity plus RE?
infinity.
Infinity. So RC is paralleled by an infinite impedance, and therefore the output impedance is RC. We will continue this on Monday.